Welcome back, students. Today's Hansen math lesson regards finding limits analytically, part 2. In this video, we'll look at when direct substitution yields 0 over 0, but to find the limit, you can use a technique of expanding, using a conjugate, or using a least common denominator. Also, please note that the PDF file I'm working off of is attached in the description section underneath this video, and an answer key in PDF is also provided so that you can check your work. So without further ado, let's get into part 2 of finding limits analytically. Okay, in part 2 of my finding limits analytically lesson, we are going to start on scenario 4. Scenarios 1 through 3 were in the prior video. Scenario 4 says if f of c equals 0 over 0 and the function looks simplified already, expand and then evaluate again. Okay, so if you look at this example here, the negative 10 has already been factored out, so factoring is not going to help us get what we need like it did in the previous scenario. So we're going to have to expand instead. Before we do that, though, let's see where we get into trouble if we try to replace h as being exactly 0. So if we plug in 0 for h, we'd have negative 10 times x plus 3h. 3 times 0 would be 0, plus 10x all over 3h. But if you plug in a 0, 3 times 0 is 0, so that's division by 0. And then in the numerator, you'd have a negative 10x and a positive 10x, which would zero out. So you do have your 0 over 0, which quite frankly doesn't tell us anything about the limit. So let's try this technique here of expansion. And what I mean by that is we're going to use the distributive property and distribute this negative 10 here to the x and to the 3h. So let me do a rewrite. We have the limit as h approaches 0, and we'll distribute. Negative 10 times x is negative 10x. Negative 10 times 3h is a negative 30h. In the numerator, right here, we also have a positive 10x. We'll bring that along, and we'll put it all over 3h. Well, let's do a rewrite. The limit as h approaches 0. Let's clean up this numerator. We have a negative 10x and a positive 10x. Those offset. So we have negative 30h over 3h. Well, let's do another rewrite and see if we can clean it up a little bit more as h approaches 0. The h's will cancel. H divided by h cancels to 1, and negative 30 divided by 3 is just negative 10. And there's no variable, so there's nothing to substitute the 0 into. So in this case, the limit as h approaches 0 is just equal to negative 10. Okay, that's as far as you can go. Now, let's take a quick peek at Desmos and see if we can verify visually why the limit might be equal to exactly negative 10. On Desmos here, you'll see the first function I have popped in here with this little red tilde is the function in question that we just looked at. And since there's essentially two variables here, there's x and h, I have h set as a slider so I can pick different values of it. You can see that the graph is linear. It's a straight line that crosses I should say it's a horizontal line that crosses the y-axis at negative 10, as you can see. And if I change the slider to make h exactly 0, it disappears because of the division by 0 problem. But any other value whatsoever I could choose for h, you always have this height of negative 10. Okay, so that's graphically a verification of the limit being negative 10. All right, here we go to the next example. All right, in our next example under scenario 4, you'll see that we have in the numerator here, we have this binomial squared. You can't factor anything out, so we're going to go the other way and we're going to expand. So we're going to have the limit as x approaches 0. And when you square this binomial, the kind of fast and efficient way to do it is you square the first term, so 4 squared is 16, and then you do twice the first times the second. So 4 times x is 4x, but you have 2 of them if you FOIL it out. So twice 4 times x is 8x. Some people say 2 times the first times the second. 2 times 4 is 8. 8 times x is 8x. Plus, you square this term, you square the x, which would be x squared. Okay, so when you square out this binomial, you get a trinomial, which is right here. And in the numerator, we still have this minus 16. So I bring that down, and this is all over x. Okay, so to rewrite, we have the limit as x approaches 0. Here you can see that we have a 16, and then down yonder we have a negative 16. Those will offset. So I have 8x plus x squared over x. I can rewrite it again, the limit as x approaches 0. Okay, now note that in your numerator, the 8x term has an x, and the x squared term obviously contains an x. So now we can factor out an x. So if we factor out an x, we pull it out of the 8x, so we just have 8 plus, if we factored out an x from x squared, that leaves us with x all over x. Now you see that we have an x on top and x on the bottom. Those will cancel out. So we have the limit as x approaches 0 of 8 plus x. Okay, now let's evaluate x at 0. Let's plug this in. So via substitution, we have 8 plus, instead of x, we're going to plug in 0. 8 plus 0 is just 8. So as x approaches 0, our limit is 8. We actually can find it instead of getting stuck with 0 over 0 right out of the gate. So the limit here is 8. And let's take a quick peek at Desmos and see if we can visually confirm why the limit would be 8. So here we are on Desmos for the previous example. You can see this one looks linear if I zoom out. If I zoom back in, as x approaches 0, let's see. Exactly at 0, the function value is undefined, but if you look just slightly to the left, I'm at 7.95, 7.97, 7.99, a little bit to the right, 8.01. You can clearly see that while it's undefined at 0, as x approaches 0, you're at a height or a function value of 8. So once again, this is a great example where you might have a hole at the function value, but you can clearly see that you still converge on a limit, in this case 8. All right, great. Let's go right back to our PDF sheet. All right, ladies and gentlemen, now that I have modeled the first 2 examples, now it's your turn. At this time, I'd ask you to pause the video and take a whack at y'all try K, L, and M. Keep in mind that I do have an answer key as a PDF under the description of this video if you need, but please try your best at y'all try K, L, and M. And when you've got those wrapped up, please hit play to proceed with the video, and we'll hit scenario 5. So I'm about to move on to scenario 5, but at this time, hit pause and knock out these y'all tries in a workmanlike manner, showing the work as I've modeled previously. Moving on to scenario 5. If f of c equals 0 over 0 again, and the function has a radical plus or minus another term, try multiplying by the conjugate, which is a term you may have seen before. Now, I will say that this lesson is quite algebra intensive, so this will sharpen your skills. The better you are at algebra, the better you will be at all types of advanced math, so hang in there. So let's take a look at this here, this first example. We have the limit as x approaches 0 of x over the square root of x plus 9 minus 3. Now, if you plug in 0, you will get 0 over 3 minus 3, which is 0 over 0. So that doesn't tell us anything about the limit. So what we'll do here is this. Notice that in the denominator of this guy, we have radical x plus 9 minus 3. We're going to multiply by its conjugate, which would be radical x plus 9. You don't change the sign inside the radical. You change the sign, easy for me to say, sign between what I'm calling term 1 and term 2. In between these two terms is a minus. So now we switch to plus, okay? So instead of square root x plus 9 minus 3, the conjugate is x plus 9 plus 3, okay? It's kind of like its buddy, its two-term buddy with the sign in the middle reversed. So that is what the conjugate is. Now, since this is not an equation, it's only an expression, we have to be careful not to change the expression. We won't change it as long as we multiply by 1. So multiplying by 1 is multiplying by anything divided by itself. So if in the denominator I have root x plus 9 plus 3, the numerator also has to be x plus 9 in the square root plus 3, okay? This is one whole because it's the same thing divided by itself, so you're not going to change the expression. Now, let's rewrite this limit as x approaches 0. And what we have is the following. We have this x here times, and I'm going to put this in parentheses to help. So we have x times the square root of x plus 9, and then the square root ends, and then plus 3. All over. Now, with these conjugates here, it's kind of like the difference of two squares. This would be like a FOIL, right? Where I'd have first, outer, inner, last. But the thing is, due to the minus 3 and the plus 3, I don't have to do the outside, the inside. I only have to do the first and the last. So the first term here, I have square root of x plus 9, and the other first term is square root of x plus 9. Root x plus 9 times root x plus 9 is just x plus 9. As you should know from previous experience, when you multiply a square root by itself, the square root essentially cancels out. So that's the first, and then the last would be negative 3 times positive 3. Negative 3 times positive 3 is negative 9, okay? So let's do one more rewrite. So we have the limit as x approaches 0. I have in the numerator x times the square root of x plus 9 plus 3. Now, you might wonder if I'm going to distribute this. I'm actually not. No usefulness usually comes out of it, so I'm going to keep it just written like that. But I am going to simplify this denominator. We have x plus 9 minus 9. So the plus 9 and the minus 9 cancel out, leaving us with just x. If I simplify this a little further, you'll notice that I have an x on numerator and an x in the denominator. Those cancel to 1. So if I rewrite this one last time, I have the limit as x approaches 0 of the square root of x plus 9 and then plus 3. So now at this point, I'm going to try to plug in the limit of 0, direct substitution, and see what happens. So now I'm going to write, let's sub in. Instead of x, let's plug in that 0. So you've got 0 plus 9, the square root of that, and then plus 3. So now we have the square root of 9 plus 3. which means that we have 3 plus 3, which is equal to 6. So the limit here turns out to be 6 by multiplying by the conjugate and doing a lot of algebra. So if you need to rewind and look back on this, please feel free to do so. But without delay, let's once again pop over to Desmos and see if we can visually verify that the limit is indeed 6. All right, so we're on Desmos looking at the previous limit problem we just solved, where the limit as x approaches 0 is 6. This does look like a square root type of a function. So as we approach 0, you can see that we are converging on a height of 6. The function value at 6 is undefined due to division by 0, but you can clearly see that we are converging at a height of 6 if it wasn't for that itty-bitty undefined hole at exactly x equals 0. So we're converging on a height of 6, which is the visual explanation of the limit. I hope this makes some sense. And let's go back to another example on scenario 5. All right, back to scenario 5. We have the limit as x approaches -1 of 5 minus root x plus 26 over x plus 1. If you plug in this limit of -1, you will get 0 over 0. So this time we have a situation where we can multiply by the conjugate in the numerator because we have a radical, we actually have 5 minus a radical x plus 26, okay? So remember, you have a term, a sign, and then a term, if you will. So we're going to change this minus between these two terms to a plus. That is going to be the conjugate. So we're going to multiply by 5, but instead of minus, plus the square root of x plus 26. And I have to divide by the same thing, so it's really like multiplying by one whole. You're not changing the value of the expression. Okay? If you want, I can put these expressions in parentheses if that helps a little bit. So now I'm going to rewrite, we have the limit as x approaches -1 of, again, this is kind of like a FOIL deal here when you multiply with the conjugate. But since you'd have a negative outside and inside of the same amounts, those cancel. So you're really only multiplying the firsts and the lasts when you have the conjugate situation. So to do that, we have 5 times 5, which is 25. And we have a negative times a positive, which is negative or minus. And the square root of x plus 26 times itself is just x plus 26, but we have to keep it in parentheses because it is a group, okay? It's minus the whole group. Very important to keep the parentheses here, extremely important. All over, let's see here, we have this x plus 1 term right here, and we're multiplying by 5 plus the square root of x plus 26. All right. So let's rewrite our limit as x approaches -1. Let's simplify this numerator a little bit. We have 25, and then we're going to subtract the 26. 25 take away 26 is going to be a -1. And we also have to distribute this minus to the x, so that's going to be a -x. Okay, we've got some good algebra work going on here. And I'm just going to recopy the denominator. There's really not going to be any good of foiling this out. It's just going to become a bigger, sloppier mess. So just write quantity x plus 1 times the quantity of 5 plus the square root of x plus 26. Now, you generally want something to cancel out here. And you might say, well, nothing cancels out because -1 minus x doesn't cancel with anything in the denominator, but it really does. You can make the numerator look like x plus 1 if you factor out a -1. So let's do a rewrite here. So let's look at, again, the limit as x approaches -1 of, what happens if you factor out a -1? If you factor out a -1, to get back to -1, you're multiplying by 1. And then since you factored out the -1, to get back to a negative x, you actually need to do positive x. Now, if you don't believe me, distribute. -1 times 1 is -1, and -1 times x is -x. So you see it works. Over, we've got x plus 1 times 5 plus the square root of x plus 26. Now, note that in another life, maybe I'll have good handwriting. This is embarrassing. Okay, we'll just leave it like that. All right, now you'll notice that 1 plus x is the same as x plus 1. You can just flip them around. They're commutative. So these cancel. So we're left with the limit as x approaches -1 of -1 over 5 plus the square root of x plus 26. Okay? Now, what happens at this point if we substitute in this limit value of -1? Okay, if we use direct substitution, what will happen? Well, let's see. We'll have, let's see, I don't want to use yellow. How about red? We'll have -1 over 5 plus, if we plug in a -1, -1 plus 26 will become root 25. So that will be -1 over 5 plus the square root of 25. That's 5 plus 5 is 10. So our limit is just a -1/10. Okay? So while we couldn't get anywhere from the outset with 0 over 0, after some algebra, we get a limit of -1/10. Okay, besides my terrible handwriting, I hope this makes some sense. Remember, you can always pause and go back and rewatch, but let's take a peek at Desmos and see if visually we can see this limit as x approaches -1 of -1/10. Okay, so we're on Desmos. This is a very odd looking graph. It's a very flattened out square root function. You can see here it doesn't begin until -26, but that makes sense because if you put in for x here something larger negative, something more negative than 26, you're undefined because then you're going to have a negative in the radical. So it starts at -26 in the domain and you move to the right. So our limit was approaching -1. So if we slide this sucker over and eventually get to -1 in the x, here we are. So approaching -1, if we hit -1, it's undefined because of the division by 0. But slightly to the left, we're at really a height, it's rounded, -0.1001. And to the right, the same thing, 0.0999. So that is your -0.1, which is your 1/10. Okay? So this is visually showing you why the limit is indeed -1/10. It's 1 over 10 negative as a decimal, or -0.1 as, well, you know what I mean, a fraction or a decimal. So there you have it, and that sums up scenario 5. So let's look at the y'all tries. For scenario 5, you have y'all try N, y'all try O, and y'all try P. If you substitute in the limit value right off the get-go, you'll see you get 0 over 0. And in each case, in these ones, it's the numerators, you have a radical minus a value or a value minus the radical. So you're going to multiply by the conjugate in a workmanlike manner as I've showed, and you should have some success. So hit pause, try your best hand at these, and when you are done, we will move on to the last scenario, scenario 6. Thank you very much. Okay, we are into the home stretch here. Scenario 6 is the final one for this lesson. Again, if you directly substitute in the limit value right out of the gate, you'll get 0 over 0. And you have fractions in the numerator. You can try to condense the numerator using common denominators, or LCD, lowest common denominator. And it's going to work very, very well. Again, it requires some algebra, and there's a lot of rewrites, so it could get kind of sloppy real fast. So let's take a look at it. In this example here, we have in the numerator, we have 1 over x plus 3, and then it subtract 1/3, okay? So our denominators are x plus 3 and 3. So if we think what would be the least common denominator, well, we need both of those terms. So it's going to be 3 times x plus 3. That would be the LCD, or the common denominator, okay? So how this is going to work is as follows. I have the limit as x approaches 0. And I'm going to write down my first fractional piece of the numerator, which is 1 over x plus 3, okay? And I'm going to put this in parentheses, and I'm going to look at the denominator part, which is x plus 3, and I'm going to compare it to this LCD here. So what doesn't it have? It has the x plus 3 portion, but it doesn't have the 3 portion. So since it needs that 3, I'm going to multiply by 3 over 3, which is like multiplying by 1 whole. So you're not affecting the value of the expression, okay? So I'm going to multiply by 3. So that's going to cause the denominator to eventually become this. Now that was just this part right here, all right? So to keep moving, now we have subtract. Now we have this 1/3 right here. So I'm going to copy down the 1/3. I'm going to put that in parentheses, and I'm going to think, what's the denominator? The denominator is 3. So if I compare it to the LCD, I've got the 3 part, but I don't have the x plus 3. So I'm going to multiply by that because I need that to have the LCD. But if I multiply the bottom by x plus 3, I have to multiply that by the top by x plus 3, so that in essence, I'm multiplying by 1 whole, and I'm not changing the value of the expression. So this is a condensing tactic for the numerator to find common denominators. And now I have to remember that this was kind of like a fraction within a fraction, right? So I'm still dividing the whole thing here by this denominator of x, okay? I know there's kind of a lot going on here, okay? I understand that, so try to stick with me. All right, so next we have the limit as x approaches 0. Now we're going to multiply, okay? So here we have a 1 on top times a 3 on top. 1 times 3 is 3 over. In the denominator here, we have x plus 3 times 3, or I'm going to say 3 times x plus 3. Okay, I'm just putting just this, this constant first, so 3 times x plus 3. All right, so there's that. We've got minus. Here I have 1 over 3 times x plus 3 over x plus 3. So numerators straight across. 1 times x plus 3 is just x plus 3 over the denominator of 3 times x plus 3, which is just that, 3 times x plus 3. Okay, so now you can see we have our common denominators, which was the goal, all over that x. All right, so at this point, if you kind of want to think about what's going on, we want the limit here as x approaches 0. If we did direct substitution and plugged in the 0 right now, we would still have division by 0, which would be inconclusive regarding finding the limit. So let's keep doing algebra and see if we can take this thing a little bit further. So I'm going to do a rewrite, the limit as x approaches 0. So now we have our common denominators in this, let me box it in yellow. In this big numerator section here, okay, we've got our common denominator. So just for this numerator section, okay, let me put in my fraction bar. Within the entire fraction, the numerator fraction has a denominator of 3 times x plus 3. And now since we have common denominators, we can combine. So now we have this 3 here, my friends, 3 minus the quantity of x plus 3, all right, all over that x. So we still have division by 0 here. We're not going to have it for long because we are about to do some simplifying. So there's a lot of rewrites here. So now we've got the limit, again, as x approaches 0. What if we do some simplifying to this numerator of the top fraction? We have 3 minus the quantity of x plus 3. So we have 3 subtract this 3. So those 3's are gone. And we're left with minus x. This minus distributes, right? So we have minus x, right? The 3's are gone because we have 3 minus 3. And then we have, so we have the negative x over 3 times the quantity x plus 3 all over, I can make that a little bit better, all over x, all right? Now, at this stage, let's get rid of this fraction inside of a fraction thing. So let me do a rewrite. We've got the limit as x approaches 0 of, well, our fraction is negative x over 3 times x plus 3. And now what are we dividing by here? We're dividing by this x. But remember, dividing is the same as multiplying by the reciprocal. So instead of dividing by x, I can multiply by 1 over x. I'll say it again. Instead of dividing by x, I can multiply by 1 over x. That's the same operation. So if we do that, what you'll see happens is this x cancels with that x. Now this is a big step here. This is going to eliminate the division by 0 problem. So if we do a rewrite one more time, we're going to have the limit as x approaches 0 of negative, and it's not a negative nothing, my friends, it's a negative 1. So we have a negative 1 over 3 times x plus 3. Okay, let me make my x a little bit better here. I think I just made it worse. All right, you guys get the drift. So at this point, now what happens if we try direct substitution? If we try direct substitution, if we sub in 0 for x, we have negative 1 over 3 times 0 plus 3. So we have negative 1 over 0 plus 3 is 3. 3 times 3 is 9. So our limit is negative 1/9. All right, so that's quite a bit of algebra. Using this common denominator method, we have a limit of negative 1/9. So finally, you probably can sense where I'm going to take this. Let's take a look at Desmos and see if we can verify as x approaches 0, a limit of negative 1/9. So over here on Desmos, for the previous example, we can see the 2 branches of this function. And we wanted the limit as x approaches negative 1, I believe it was. Or was it 0? No, we wanted the limit as x approaches 0. So if we approach 0, you'll see that the function value is undefined. But what about to either side? Well, let's zoom in here. What about to either side of 0? Okay, so it's undefined exactly at 0, but just slightly to the left, we're at negative 0.1111, and just to the right, we're at negative 0.1111. Well, 0.1 repeating is 1/9. So there it is. There is your negative 1/9 verified graphically. Well, ladies and gentlemen, if this felt like a tough one to you, you're in good company. Felt a little bit tough to me as well. So that concludes scenario 6, using common denominators. I want you to try, y'all try Q and y'all try R. Those are the final 2 examples. Do the best you can, and remember, I did put the answer key right on the YouTube channel in the description of this video section. And that wraps up another installment for today. So thank you very much for your support of my Hanson Math YouTube channel. I hope this lesson did make some sense as we continue our pursuit of solving limits analytically as we march closer and closer to calculus, namely something called the derivative. So thanks again. I hope you did well and have a great day.